to your Tuesday edition of Learn Extra Live. I'm so loud because I'm so excited. I haven't been here in ages. I am Looney, and that is John. Hi, John.
Hi, everyone. Hi, Looney. How are you doing?
I'm good. How are you doing, John?
Yeah, really great today. Now, grade 10s, we've got a great lesson in store for you, and we've got some fantastic news to give to you as well. So, Looney, let's get on with the original announcements, and then we'll get into the show.
Okay, cool. Mindsetters, if you've forgotten and if we have new mindsetters, welcome, guys. All you need to do is hit us up on Facebook. Our page is facebook.com/learnextra. Our Twitter handle is @learnextra, and you can download all the show notes, the videos, and the schedules on learn.mindset.co.za. And if you want to win yourself this awesome Casio calculator, all you need to do is complete the test yourself questions. We do have a link on our Facebook page. All the instructions are there. All you need to do is fill in all the questions, complete the questions, submit your entry, and you'll stand a chance to win this awesome Casio calculator. And remember, guys, entries do close next week Tuesday. So you have until next week Tuesday at 8 in the morning to enter this awesome competition. So if you want to win yourself a calculator, it's exam time coming up very soon, and you need a calculator even in class, enter this competition, guys. John?
Thanks, Looney. Now, guys, today we are dealing with the most amazing topic. We're dealing with reactions in solution. When we talk about that, you might say to me, that's got nothing to do with what I do every day. And yet it has. Looney, what's the most important thing that we can drink, that we depend on in everyday life?
Water.
Water.
Yes.
Guys, today's lesson is all about water. And when you start to think about water, begin to recognize how special it is. And so that's exactly what we're going to be doing today. Let's focus our attention. We're going to explain as we go through this session the structure and the properties of water. We're going to look and discuss the processes of forming something called an aqueous solution. And we're going to consider conductivity as a measure of how things dissolve in water, how soluble things are. But before we get into all that, I want to introduce you to the challenge question. Now, today's challenge question is really special, and I hope that it gets you thinking. I hope that it doesn't just sit there as a challenge question, but that it actually gets you thinking about real things. And I've got a little surprise to help you with that. So let's read it together. It tells us that a sample of water is taken from a stream in the Middle Olifants catchment area. Now, why we chose the Middle Olifants catchment area will be clear just now. The sample is found to have high levels of compounds found in fertilizers, and it also has high levels of bacteria and undissolved organic products. The question that we need to ask ourselves is, what actions would you recommend to the water managers in this catchment area? Now, guys, there is so much that you could talk about there. And there are so many things that you could do as we think about the importance of water to our lives and the way that water is used and how important it is and all of those things that we could spend a whole week talking about it. But we've got a better way of doing that. We've joined together with a group of people who are running the National Water Game, South African Water Game. And it's the Water Game Challenge for 2014. And here's the very nice thing. If you go to this website, you won't be able to answer the challenge question, but the website is there. It's watergame.co.za. Looney will post the link on the page, and I'm sure it's on the page already. I want to just show you what it looks like, because here is the opportunity, watergame.co.za. It tells you a whole lot of information about the water game, and it's based in the catchment area of the Middle Olifants region. This is real science that is behind this game. And they've turned it into a competition, a real engineering model of what happens in a catchment area, turned it into a game, and they've started playing on Friday, last Friday, not so long ago. So you can enter this game, and there's some great prizes to be won. The winner, and you can play it as many times as you like. So you get a login, register. The winner that gets the highest score in the next month gets 5,000 Rand cash. Then the next runner-up, the second person, gets 3,000 and the third place person gets 2,000. So there's great prizes, but there are more prizes than it. As you play the game, there's airtime vouchers, and there's a whole lot of other things that you can read about. There's a draw for somebody going to one of the sand parks. You can play it actually in the Kruger Park, which is close to where this catchment area is. And then the University of KZN have also are offering a bursary. But that's all information that you can read on the page. I want to just give you one little thing, that if you start to register, it does take a little bit of time to load. So if your screen goes white, don't panic. Just let it do its thing, and it will come up, and very soon you'll be playing the water game. So get in there. It's a turn-based game, which means you've got 12 turns to get the highest score. Then it ends and starts back at the beginning, and you play again. See if you can beat your own score. Okay, get going with that. Make sure you enter. It's an online game. I don't think you can play it on a mobile device. Get onto a computer that's linked to a network that's got fairly good bandwidth, and you will be away for learning about water and finding out a whole lot of things about water. There's a question for you to think about during this show. What could we do for a river in this state? Water from a river that's got lots of fertilizer, got organic waste in it, got high bacteria. Well, let's think about it. And let's first of all, though, get into our summary that might help us give some of those answers to that very important question. So we're talking about water, and the first thing I want to mention is that water is very special. Water is one of the most amazing molecules because it has many unique properties, very different to other things, and so we use it, and it's more than 70% of our bodies are made up of water. The Earth stands out amongst the planets as the reason for life is because there's water here. And so many of these unusual properties, its boiling point, its melting point, the fact that when it freezes, it floats, these are due to the structure and the shape of the water molecule. So let's explore for a minute what we think about the structure and shape of the water molecule. Now, in science, we can do build up some models of the water molecule. We're not going to go into very advanced models, but I just want to revise one little thing with you, and that is, let's draw the Lewis diagram for a water molecule. And that will give us some information about why water is the way it is. So when we take a look at water, we recognize the chemical formula of water is H2O. So I'm going to draw the Lewis diagram. The first thing I'm going to do is I'm going to say, I need to get to oxygen. Now, oxygen is the element on the periodic table with an atomic number of 8. But the first 2 electrons in the inner shell, the next 6 electrons are in the valence shell. So when we draw the Lewis diagram, we must draw just the valence electrons. So I'm going to draw 2 of them together, and then I'll draw the next 3 separate. And the reason for that is we're applying Hund's rule. Then we've got 5 altogether at the moment. We can put the next one over here, next to the pairs. So we've got 2 pairs of electrons from the oxygen atom, and we call those lone pairs. And they play a very important role in the structure and the shape of the water molecule. Because they have got this high electron cloud, or a dense electron cloud, 2 pairs of electrons, they want to get as far away from each other as possible. And so that causes the water molecule to bend a little bit. But notice what's happening at the other end of the water molecule. Over here, we've got an oxygen, an electron on the oxygen that's on its own at the bottom here. That electron is sitting on its own, and it has a capacity to take another electron. So it's a single unpaired electron. When we see single unpaired electrons, we know these are bonding potential. They want to bond. They want to get to a complete outer energy level, a complete valence structure. So we're at 6. We want to get to 8 because 8 will give us a structure and electron configuration like a noble gas. So what are we going to do? Well, along comes hydrogen, and hydrogen says to us, guys, I've got an electron, and I'm happy for you to share this electron. And so the hydrogen electron, I'm going to just draw it in a different color and a different shape. I'm going to draw it as a dot. The hydrogen electron sits there as those pink dots, and they share with the oxygen. So we've got 2 single covalent bonds sharing electrons quite happily with the oxygen. But now, I need you to understand something. Hydrogen is very small, okay? And oxygen, the mass of a hydrogen atom, 1 atomic mass unit, oxygen 16, okay? Hydrogen 1 electron, and oxygen is desperate to get 2 electrons to become stable. Hydrogen hasn't got much fight in this because it's got 1 proton, 1 electron, whereas oxygen has got 8 protons, 8 electrons, and it wants to get another 1. In fact, it wants to get another 2. So what happens here is that these bond pairs, this bond pair of electrons, gets pulled towards the oxygen. It gets pulled away. So it's a bit like a tug of war, okay? And if you're little, you've only got one thing, it's easy to lose it. The oxygen pulls it away, doesn't lose it totally, just pulls it towards it. So the end result of that is that this end becomes slightly negatively charged. Sorry, this end loses the electron, so it becomes slightly positively charged. Slightly positively charged, which means that the other end where these lone pairs are become slightly negatively charged. Now you'll see I've written a funny squiggle that is called a delta, a little D with a tail on it, and that's saying slightly charged, okay? So at the one end, the lone pair end, we've got a negative charge, and at the other end, we've got a positive charge. So water is what we call a dipole. It's a dipole. It's got 2 ends that are opposite in their charges. Now, guys, it's really important that you understand this. The structure of the water molecule and the shape of the water molecule is such that it is a very strong dipole. And what you can see is that if I have one water molecule like that, then if I have more than one, and I'm going to just quickly draw it as a little shape, then what can you say if I bring another one on? The little circles represent the hydrogen, so that's where the positives are. Then I think you can see that the negative ends, where the lone pairs are going to want to line up like that. And a positive charge is going to want to line up. And between these molecules, there will be a little bit of an interaction. And sometimes that interaction is really strong. And that's why water has such a high melting point and boiling point compared to other molecules that have similar masses. Because of these strong forces between the molecules, we call those intermolecular forces. And I'm sure you've heard about those. So I want you to recognize this is a dipole. We say it is a polar molecule. Polar, not because it comes from the North Pole or the South Pole, but simply because it's got intermolecular forces and it is recognizing that they come from being poles. A pole being one end as being delta negative and the other end as being delta positive. And then on this molecule, we've got delta negative and delta positive. And the positive ends are going to attract the negative ends, all about electrostatics. So this is a polar molecule. Now, if we've got that idea, and that's the most important idea, then we recognize that water can do a whole lot of things for us. Not only does ice float because of this arrangement and the intermolecular forces, but water can play the role of dissolving things. And that's what we're talking about, making solutions. So the very first thing I want to remind you about is there are 3 little words that you need to remember. A solute, when we're talking about dissolving, is usually the solid that is being dissolved, but it can also be a gas. In fact, it can also be a liquid. But usually, the most common solutes are the solids. So when we take sugar and put it into a glass of water, hot water to make tea, we are dissolving. The sugar is the solute. The water is the liquid that does the dissolving. This does the action of dissolving, does the dissolving. And the end result is called a solution. So this is a solute plus a solvent. When they mix together, they form a mixture where there is no difference. You can't pick up the difference. You can't see, there's the little sugar granule. No, you can't see it. It actually seems to disappear. If you take some potassium permanganate crystals that are tiny little crystals, they're purple in color, you put them into a beaker of water, very soon you'll see little black spots at the bottom or dark purple spots at the bottom of the beaker. But very soon you mix them around a little bit and let them, color spreads through the clear liquid, colorless liquid, and it becomes a clear purple solution. So there are no boundaries. So it becomes a mixture that we can see, but it's still there. So how do I know it's there? Well, if I take a beaker and have some sugar in the water, and I put my finger in, and I lick my finger, what am I going to do? I'm going to taste the sugar. Can't see the sugar, it's too small. It's broken up into tiny, tiny little pieces. That's the process of dissolving. Okay, let's move on. Very quickly, aqueous solutions. When we have salt dissolving in water, we say sodium chloride is an ionic solid because water is a universal solvent. It can dissolve almost anything. There are some exceptions, and we'll hopefully deal with those. But water dissolves ionic things really nicely. I want to show this to you. Sodium chloride can be written as NaCl, and it's as a solid. And it can break apart to form separate ions, just simply move apart from each other, that we would write in an equation like this. So what we've got is sodium ions with that AQ written down. What's that saying? So this is a chemical equation that you would see on the dissolving process. Let me explain to you what's actually happening. So what actually happens is we've got a sodium ion, and I just want to get a little over there, and a chloride ion over there, and a sodium ion over here. And I'm just drawing it in 2D, and I'm just going to do two of them like that. They actually form up in a crystal lattice, but now what happens is we get our water molecule. The water comes in over here. This was our negative chloride ion, and this one was our positive sodium ion. So our water molecule comes along and it sits over there like that. And we literally get hundreds of thousands of water molecules that sit over here. And there are forces of attraction, sure, between there, and there are forces of attraction. But if I get lots and lots of water molecules packing around there, it's a bit like a dog pile. It starts to pull these ones away. And the forces between the water, those forces, and those forces are in a pull with each other. So these ones are trying to pull it away, these ones are trying to pull it that way, and keep it in the solution. Who's going to win? Well, eventually the water will win because there are just too many of them. And the same way around this little sodium ion over here, that little sodium ion, if I can pull it apart, it will drift off on its own and be surrounded by little bits of water, little water molecules. In this case, there'll be the negative end over there, the oxygen end over there, because we have that picture. And we call these kind of little units that are hydrated. They've got water around them. That's the picture for ionic. Now, we haven't got time to do the rest of that. We'll do them in some questions. I think we've come to the time for a break. So, Luni, over to you.
All right. right, Mindsetters, I hope you downloaded the notes. They are on our Facebook page. You're going through the questions as John is explaining. You're making little notes. You've got your pencil next to you. And with that said, let's take a very quick break and we'll see you straight after this. Welcome back, Mindsetters, from that break. Very quick shout out to Lungelo, Nokolo, Moya, Habo, and Mishak. Thank you so much for tuning in, guys, and for joining us and for having a little something to say on our Facebook page. Tell all your friends to hit us up as well, and on Twitter at LearnExtra, and Facebook, facebook.com/LearnExtra. Tell them to watch LearnExtra Live. It's a very nice show to watch. John?
Thank you, Ginny. I'm so glad you're enjoying yourself there. And thanks, guys, for chatting to us. So we'll be ready to take all your questions, but more so, I want to remind you about our challenge question. Get on the page and see what suggestions you've got to answer this question. River sample, bad water, fertilizer, organic waste, a whole lot of things. What do you recommend to the water management? If you don't have any ideas, go to the water challenge. Get involved, run the competition, and you could be a winner. You could learn a whole lot too. Okay, so having established now that water has a particular shape and structure and that it is a polar molecule having a dipole meaning two ends that are oppositely charged, one positive end, one negative end, what we recognize is that water is very good for dissolving things. We did the example of sodium chloride. But what other things can water dissolve? And how can we illustrate those? Well, let's look at question 1. It says to us, draw a picture or a diagram, symbolic representation, to show the micro view of an aqueous solution formed when the solute is copper 2 chloride, ammonia, and lead chloride. Okay, so we're going to draw 3 little pictures. The first one is for copper 2 chloride. Now, what do we know about copper 2 chloride? Well, the first thing that I know that copper 2 chloride is a salt, and it has the formula CuCl2. It is ionic, so when it dissolves, it's going to dissociate. The positive ions are going to be left surrounded by little water molecules, and the chloride ions, and there are 2 of those, are going to be hydrated as well. So that's the chemical equation, which I didn't really ask you for, but it's a nice way to think about it. How are we going to picture this equation? Draw a picture of this part of the equation. We're not interested in that, we're interested in this part. So what's it going to look like under a microview? I'll tell you what I'm going to do. I'm going to draw the copper as little orange blobs, and I'm going to draw the chlorine as little white circles. Recognize that this is positive, recognize that that's negative, and then what we're going to do is we're going to draw in the water around them. So around the positively charged water, copper ion, we're going to get, and there was 2 pluses over here, sorry I didn't put those in, we're going to draw the water molecules, and you could draw 3 or 4 or 5 or 6, it doesn't really matter. But the idea is that they're surrounding them. But look what happens on the other side. Here is our little water molecule, and it's now going the other way. Why is that? Well, because it's attaching to a negative ion. It's surrounding a negative ion. We're going to squeeze in another water molecule over here. We're going to put in the positive ends closest to that, positive ends closest to that one, positive ends closest to that one, and so on. So what you can see is that the water molecule forms this bubble. It kind of like wraps up the ions. And that's why we call them hydrated ions. And in the equation, that's why we do this, AQ. Because anything that's dissolved in water is given the name of an aqueous solution. Aqua. If you think about aquarobics, what other words can you think of, Looney, that have the word aqua in it?
Aqueous cream.
Aqueous cream, very good. Cream that you rub, that's so nice when it gets dry and you want to rehydrate you. It has aqueous or aqua. Think about some aquanaut There are a whole lot of other words that we could talk about as being aqueous. Now, remember, this was ionic, so we recognized we've done one like that. But this one, ammonia, it's NH3. It's a covalent molecule. But we know that ammonia is polar. You should know this. It is a polar molecule. And here's a little bit of a rule that starts to come out when we talk about dissolving. Things that are of the same nature. So if we've got something that's polar, then it will dissolve in another substance that is also polar. We say like dissolves like. So ammonia, covalently bonded. So if we're going to draw the equation first of all. Ammonia now actually interacts with water in a slightly different way. It doesn't just split apart to form nitrogen and hydrogen, but it forms the ammonium ion. There are no ions here. This is usually a gas, and water is usually a liquid, and it forms ammonium ions. We're going to say that's AQ. And then on this side, we're going to say what's left over is OH minus, and that's also AQ. So what's actually happened, guys, is that ions have formed. In the dissolving process, we have made ions. This process is not called dissociation, because when we had, think about, you form an association. You join a soccer club. You become a member. You associate yourself. When you want to leave, you say you dissociate. You distance yourself. You don't agree with their politics anymore. So you dissociate yourself. You move away. For ionic solids, dissolving in water, they undergo dissociation. Association. For covalent substances like ammonia, they undergo ionization. And they can ask you both of those terms. You need to know them. So please be very aware of the difference. But if we were to draw a picture, well, it would be more or less the same sort of thing, except that the geometry is slightly different. So let's just draw a very brief one, and we'll try and get it in. We'll say that's the ammonia, and let's put an oxygen with it, or a water molecule. We want an extra hydrogen. Remember what we said? It needed to be in the solution. So we wanted an ammonium ion, and that's positive overall. And over here, we're going to have another oxygen. We're going to have an oxygen with a hydrogen attached to it. Let's make them all the same. And in between these, this is negatively charged. We put those as negatively charged. In between those, we're going to have some water molecules. And the water molecules are just normal water molecules that haven't lost anything. So in this case, you're going to have water molecule surrounding it like a little tube, like a little bubble, and we get those forming in solution. Now you'll notice that in this case, we've got a lot more water molecules than ammonium. Remember, this was your nitrogen. There's your ammonium with the 4 dots around it, the 4 hydrogens. The other things are the water molecules that are surrounding it. Ammonia is covalent, it forms ions, it dissolves. You can't see a little bunch of ammonia molecules creeping up in a corner. No, they're not allowed to do that. They stay by themselves. Now, the last one that we have to look at is this one. Now, unfortunately, we didn't have time to discuss it in the summary, but we might as well discuss it now. Lead 2 chloride. Guys, it's a metal and a non-metal. That tells us that it's a salt. If it's a salt, its bonding is primarily ionic. So we've got lead ions and chloride ions in a crystal lattice. The trouble with most with a lot of ions, with a lot of salts and crystals, is that they're actually quite hard to dissolve. Lots of things water will dissolve. So like all nitrates, all group 1 and some of group 2 salts of those elements, water dissolves. But there are some that it will not dissolve. Like most carbonates, water doesn't dissolve. Sulfates, most sulfates will be soluble except for some of the heavy metals like mercury, barium, and lead. And chlorides, most chlorides are soluble except for silver, lead, and mercury. So you can see that there's a pattern here. We've got lead chloride. And what we're going to say is it doesn't dissolve. It is insoluble in water. So it will not dissolve in water. Why? Why won't it dissolve in water? Well, because the forces between the lead and the chloride are stronger than millions and millions of water molecules tugging at each of those little ions. Can't break them down. They're too tightly bound. So if we were to draw a picture, what we'd recognize, first of all, if we were asked to do an equation, we would say PbCl2 and plus water basically doesn't do it. There's no reaction. There's no reaction. Nothing happens. That's solid. That's a liquid. There might be a very, very slight 1 in a billionth of one of these break apart. But in general, nothing. So what we're going to do is we're going to represent it. We're going to say, well, there's lots of water. And they would be surrounding this clump of ions. And those clump of ions make that one the lead one, make this one the chloride one. And we'd recognize the 2 chlorides for every lead. And they're just going to stay very tightly mashed together in a lovely lattice. Okay? They're not going to break apart. They're going to stay in their solid form. Forces are too strong. Right. So, just to summarize, water is a solvent, sometimes called the universal solvent, can dissolve ionic things, solutes, can dissolve covalently bonded substances as well, particularly polar covalently bonded substances. Water is very polar, but it can dissolve even a slightly polar substance. Ammonia is also very polar, so it dissolves very easily in water. But now we have to ask the question that comes into the second, to my next slide, my next question, if we can get to there. What about substances that are non-polar? Now, oil, crude oil, is made up of a whole lot of hydrocarbons. And those hydrocarbons, organic molecules that are made from carbon and hydrogen, they are non-polar. See, the board has done its own thing. I just want to make a mention of this, that these are non-polar molecules. And what we're told is that they cause environmental damage when they spill. And what we have to do is describe how you would clean up an oil spill using your knowledge of water and oil. So I've given you a hint. What could we do? What do we know about water and oil? Well, the first thing that you would say to me from your experience, and I'm sure, Luni, you might want to chip in here if you want, say a few words about what happens if we put water and oil together.
They don't
Any
mix.
idea?
They don't mix.
They don't mix. Luni, you must speak up a bit.
They don't mix, John.
Yeah, thank you. Water sits at the bottom
Yes.
and oil
floats.
floats on the top. So there we've got the oil. Okay. Now, why is that? Well, there's one reason that you might remember from earlier grades is that oil has a low density, generally. And it has a lower density than water. But that's not the reason that we're worried about. Yes, that will have some contributing factor. The other factor is that oil molecules like to stick together to oil molecules. And water molecules like to stick together to water molecules. And this, because the oil molecules are very large, they have lots of even though the forces are weaker, there are lots of forces. There are lots of intermolecular forces. Intermolecular forces. So if we are imagining water there's been an oil spill by a tanker and it's in the sea, what we'll recognize is the oil floats in the water. It doesn't mix. it blocks out the sunlight, and that can cause really serious problems for the ocean life that's in that area, because they get covered in the oil. The water's not cleaning it off, and they die because they're absorbing oxygen from the seawater, and they can't absorb it because their gills get clogged up with oil. So that's the very serious thing. So if we have to try and break this apart, there are two things we're going to do. The first thing we're going to need to do is use this fact that oil and water have different densities. The density of water is 1, and so it is quite useful. It's taken as 1 gram per centimeter cubed. You can change the units, but it's the standard. Does it float or sink? In this case, water is more dense. It's more dense. So what we can do is we can scoop off the oil. And so we come along with things that actually act like combine harvesters, and they pull the oil together, floats like a fishing net that pulls the oil together. Once you've got rid of the whole lot of oil, now you want to get rid of the oil that's on the birds. So you can scrape it off. You can try and scrape it off the plants. It's not going to help very much. We try and do that. But because it gets right into the skin of the fish and all that sort of thing. The feathers birds can't fly. It gets really gummed up. The oil, the water just isn't washing it off. So what we've got to do, and this is the interesting thing, is we've got to add something called a detergent. A detergent. Remember what I said to you. Oil is non-polar. And I also said to you, like dissolves like. So now a detergent is something like a soap. And I'm just going to schematically draw this. Soap has a very long tail. And at this end, it's got a charge, for example. And this end, it is non-polar. So at this end, it has got a pole, so it is charged. It might even be dipole. So we can say that it's polar. So we take this bubble of soap, small amount of soap or detergent, and we say to ourselves, what's going to happen to my oil? My oil is non-polar. So if along comes an oil molecule here, and another oil molecule is attached to it over there, and there's a force between those two, what can we say about the non-polar tail, the green one and the yellow one? Well, there's going to be a force of attraction. And it's possible that this tail can start to weaken this interaction over here. And so the oil gets dissolved in the non-polar tail. Just undo that and say that we're going to get some dissolving over here. This is happening in the solution. This is happening when you go and wash your greasy dishes tonight. In the basin, if you've had some nice boerewors or you've had some steak or bacon and it's got lots of fat that's remained in the pan, you're wanting to wash it off, you add some of that special green stuff into the hot water. The end of that green stuff takes up the fats and the non-polar stuff. And now it gets stuck to it. It's like putting a feather into honey. The honey gets onto the feather. Now it's stuck there. And then what happens to this end? This end here gets pulled in by the water. So if this was positive, then you would get water sitting like that. And if this end was negative, we get water sitting like that. Because the big end, the big molecule, the oxygen is where the lone pairs are, that's where it's negative. The small little ones, that's where it's delta positive. So that's how it would surround it. And this whole thing then becomes dissolved in water. So the oil dissolves. So by adding a detergent, we can clean up the mess. And that's exactly what they do. They add things like these. They don't go and take your green washing soap into the sea. That doesn't help because there are other things that are in the sea like salt. Salt water isn't very good for making a lather. But hopefully you can see how this dissolving process helps us to clean up polluted water. So we can use it for dissolving ionic solids, we can use it for dissolving non-polar solids, we can use it for dissolving covalently bonded solids. Water is amazing. With that, Lily, over to you.
All right, mindsetters, go grab yourself a glass of water, go get some fresh air, and we'll see you straight after this break. Welcome back, guys. I hope you're still enjoying the lesson. You're nice and refreshed. You've been drinking your water and your juice, and you've been writing down all the notes that John has been giving you. And now, John, we have some questions.
Okay, I tell you what, shall we do the challenge question first?
All right, that's cool.
So let's quickly, and I'm not going to take along because Looney's told me there are a whole lot of questions.
Okay.
But let's do some of the challenge questions. And I really would like you to think about this challenge question over the next week. I know it's not on Facebook at the moment. I'm going to post it as soon as I get out of studio. Okay? And I would like you to think about what you would do. And let's have a discussion about it next Tuesday afternoon. Okay? So, what advice would you give? So, let's deal with the first thing. The first thing, and I'm not going to do all of them. The first thing is there's lots of fertilizers. Now, fertilizers are generally made from dissolved nutrients. They include things called phosphates. They include things called nitrates. Remember, all nitrates are very soluble. But if we have too much of these nitrates in the water, it can cause a serious problem. One of those problems you'll learn about in life sciences and later in physical sciences, call it eutrophication. The water gets so rich with this nutrient, causes an algae bloom, and then the bacteria can't, the algae block out all the sunlight, and oxygen can't get to the bottom, and so the fish die, basically. Not a good idea. So what should we be doing about this dissolved substance? It's very difficult once something is dissolved to undo it. The only way that we can do it, and it's the way people recover sea salt that you put on your food from the sea, is to put it into a big pan and let the water evaporate. Now that's one solution. But we can't do that for a river that's feeding a community. So maybe we've got to do something to stop the fertilizers getting into the water. And so that's where I'm going to leave it. High levels of bacteria. Well, bacteria usually form when we get untreated sewage put into the stream. So we've got to do a process there in the same way. How are we going to help people and help the river survive if we carry on dumping stuff into the river? Well, you think about that one. The last one, undissolved organic products. Now, organic products are those things that are non-polar. So here we've got a problem. We're going to have to do some treatment. We're going to have to add stuff to it. The more chemicals, though, that we add to a river, a flowing river, it can have a negative effect. So it's not a very bright picture, but the biggest thing is that I think you can deal with the root of the problem. Go back to say, where do things come from? And give us some action steps of what you would recommend for this challenge problem. We'll pick it up again next week and we'll take your responses on that as well. Is that okay, Ludi?
Yes, that's fine.
Okay, let's go to some of your questions now.
Okay, this one is from Rochizwa Varovi. Why is oil a non-polar?
Okay. You perhaps won't know this, and that's why I gave you that information. Oil is made from a set of things that are called hydrocarbons. You're going to learn about these from a little bit in grade 11, but mainly in grade 12. Hydrocarbons are known as organic molecules. And basically, they are made up of these very long chains of carbon, bonded to carbon, and hydrogen. So something like that is how we would represent it. Carbon has 4 bonds, and it's able to make these very long chains. And I've just drawn 4 of them, and I'm not even going to tell you the name of this one, but they can have thousands and hundreds of names in them. But the basic thing that you need to know here is that there's not, the electrons are evenly distributed. Okay? There's an even distribution, equal distribution of electrons. And if there's an equal distribution of electrons, then the molecule will be nonpolar. So one that you should know is something like iodine. Let's have a look. Iodine, I2. That means you've got one iodine over here and another iodine bonded to there. And there's not a difference in size. It's not like hydrogen and chlorine. One was little and one was big. They have to share that pair of electrons equally. These are known as nonpolar molecules. Okay. There are other reasons that we can give, but basically because of the even distribution and the shape of the molecule, oil with very long chains would be nonpolar. Okay.
Okay, and then from Lihlohonolo Lamasiza, how will you see that a particular compound will not dissolve?
Okay, it's a very good question. So what we need to do, and we'll do some of this next week, is there are a set of rules that are called solubility rules. And we will use the solubility rules to determine whether something will dissolve or whether it won't. For the moment, I'm just going to say to you that you know that in terms of the inorganic substances and salts, all nitrates dissolve. And you can also say, the other easy one is that all group 1 salts dissolve. You have to, unfortunately, learn these rules. Learn those 2, and let me add a third one. All carbonates, except group 1. Group 1 and ammonium. Ammonium is included in that. Do not dissolve. Do not dissolve. So there are the 3 main ones. Unfortunately, this is something that you can do by experiment. Record your data, but you have to learn it. Okay? There are some subsections to these rules, and we'll deal with those next time. That's for the salts. But if you're given something that you don't know, you have no idea, then what you need to think about is the following, that like dissolves like. So if something is nonpolar, and it's very nonpolar and very big, then it will not dissolve in water. If it is covalently bonded, chances are it will dissolve in water. And if it is covalently bonded and polar, it will definitely dissolve in water. If it is ionically bonded, in most cases it will dissolve, except for those very insoluble salts. Even then we get a little bit of dissolving. So I think that's answered that question.
All right, and then from Lungelo patient, do all substances have H2O?
Okay, no, not all substances have H2O. All living substances have H2O. Yeah, we can't live without water. Water is part of plants, it's part of animals, it's everywhere that makes up life. They're even looking on Mars to try and find some ice crystals to see if there was any evidence of once there might have been some water on Mars. At the moment, haven't found very much evidence that there's water on Mars, so we haven't made a final decision about whether there was anything. Might have been, but we don't know. There was, very small. Okay, so not all substances. So for example, gold doesn't have water in it. Okay, and something like gold is a metal, it won't dissolve in water. We're not dealing with those type of things at the moment. Okay, next one.
I don't think we have time to take another question.
We don't have time. Oh, guys, I'm so sad to remember your challenge question for the week, and remember, get playing the water game. It's going to be a lot of fun, and of course, there are lots of prizes. If the screen goes white, just leave it. Wait until the thing installs. Luni, great to being with you.
All right, thank you so much, John. Mindsetters, remember that I have posted all the information about the water game on our Facebook page. You'll see all the amazing prizes that you can win. Remember to hit us up on Facebook and on Twitter. But if we don't get to all your questions, help desk. But from us, goodbye.